Good morning, good evening, good afternoon. Welcome, welcome, welcome. This is going to be a fun one. Brian's already frustrated, and I didn't look up a goddamn thing.
Oh, you're right. I'm already frustrated.
Sometimes, physicists and, you know, physics get chemists.
Oh, Mandy, I am not a
yeah.
waifu. I'm a husbando, trust me.
Husbandova.
So it's the opposite of waifu for women. It's the husbando.
Yes, yes. So tonight we're going to be talking about Lightspeed and why it makes no sense.
True.
And why it frustrates people like chemists.
Very much so.
Yeah, I mean it's completely foreign to most people and most things. But yeah, when you have a physics and engineering background, you kind of get to know Lightspeed a little bit. So, which makes us the superior science, always. But I mean, what the hell are you laughing about?
Fucking look at the fucking super chat you just got. I just swore. I'm sorry.
I just said I started the third word out of my mouth was a swear word.
Oh, well, good.
Apparently, YouTube made it so we can now gift memberships to our crowd. So Merry Christmas, everybody.
Oh, I hope I get one.
Daisy Girl, Little Dog, Peanuts Nana, Murph Turf, and Sarah P. Nope, you suck, Bry. You don't show up enough.
I actually pay for my sub.
Yeah, I think you are a member already.
I am a member. I paid for it.
So, Comer, apparently it doesn't charge us. So
That's super nice.
Yeah,
so those who didn't get it, you're missing out. So you better buy one.
I have a couple more, and I can certainly throw some more out. So you get the emotes, the Mighty Me emotes, which include Donald Trump thumbs up, an alien guy, an astronaut. I don't remember. SpaceX rocket, Xcomer's Amerimeat logo that he made me, me on a pirate ship on fire. I think that's me and me. So, yeah. Hey, what's up, Bry?
Hey.
All right, so let's get into it, and we'll say hello. First, but you probably cheated. You probably cheated because you're a Fed. So
has a backdoor in because the Fed backdoor.
Yeah, the Fed backdoor. Dog Mama, hello. Dog Mama's member for 4 months. Merry Christmas, Mighty Meat and Brian. Have a good stream. Thank you.
Thanks,
you as
Dog
well.
Mama.
Ghost Street. I already said hi. Damn it, you came in twice. A little bit. I should have just started right in the middle of it. He was so pissed because he was 200 million miles per hour off. Thereabout. Yeah.
No, billion miles per hour.
Oh,
no, million.
Okay.
No, you're right, million.
No, yeah, I thought so. 200 million miles per hour. So it was fun. It was fun. Brian, what's up, buddy? Will Call, what's going on, man? Mandy, hello. Brian is a waifu. Linda, hello. Goddamn waifu picture, Brian.
In the words of General Akbar, it's a trap.
Oh, for one of our friends in his gaming history. Eh? We'll get to that. Ironically, so it would depend on where it's at, but yeah, we'll get into that for sure. I'll come back to that comment. I gifted 5 Mighty Meat memberships. I think I have 5 more. I just don't know how to fucking get to them. So, do I just do it again? Yeah, plug it.
Yeah, you just do it again.
There we go. It only allows you 10, but whatever. So there's another Christmas. 5. Merry Christmas, everybody.
Hey, Crystal's here apparently too. You can't hide from us.
Michael Burke, Wilcom Magic, Mandy Kravich, and Crystal Pontak, and Just Cause. So,
Insanity.
Hey, Digger, how are you? Are you guys still streaming?
Hi, Digger.
This is free as well. It is. But thanks for being a member. Michael, what's up, buddy? I remember seeing a video somewhere that we haven't measured the speed of light in one direction, but only in two directions there and back. Hope you all figured out how to measure it. So we're gonna get into that too.
Kill me.
Because it is. Brian's a member for 6 months, 100% free. You wasted your member chat on that when you could have just said it.
True.
Joke's on you. All right. Are you guys still streaming? Hey, no worries. Merry Christmas, Sarah. Good to see you. Yeah, you do, Bobby. That's what you call irony. It's what you call ironic. There's me again. Yeah, now you remember. There's the guy we were talking about. Space is fake, and there's only turtle. What's up, Snafu? Hey, Rose.
Oh, hi, babe.
She came to get
I'm
to
so
see you get
sorry.
slaughtered.
Oh no, she's been texting me. Oh no.
Uh-oh.
All right, boys, it's not gonna be a Merry Christmas for me, I guess.
No problem, buddy. Good to see you. Billy Baby. No worries. Hey, man. And I think that is... There we go. Merry Christmas, everyone. Merry Christmas to you all as well. Good to see everybody. So Lightspeed. Lightspeed is this big, chaotic thing that often trips people up. It's right... So... Right off the bat, we're going to waffle. So I'm going to tell you what the textbook definition of things are. So the textbook says it's 300,000 kilometers per second. So the speed that of distance that light can travel in a vacuum is 300,000 kilometers per second. Now, then we add into, it's not really 300,000, it's more like 298.9. And that's in a perfect system. And like Michael said, we haven't really measured it. We get into the fact that the medium that we're measuring the light through, what's that? What is how do we know the exact distance? And then you get into so many other factors. So we're going to kind of get into that, and Brian and I are going to talk through it.
We'll do our best.
Yeah, well, yeah, metrics always using the threes. Yeah. So light speed is not a constant. It is very much up for debate. It is very fluid. Depending on what fluid, it can be very many different numbers. So, damn, dude. Merry Christmas to the guy who deals with my crap. Who's that? Thanks, Bri. I appreciate you, brother.
You're welcome. Merry Christmas, brother.
What is Christmas be about the speed of light? I'm going to tie that in too, because supposedly this Saint Nick dude flies at the speed of light to get everybody's packages, and
Faster.
that just doesn't even work out.
With all his mass.
Right, with all his mass. So another thing that I destroyed Brian on when he tried to show me up on my own Apollo stream the other night is, we can accelerate stuff to the speed of light. But we can't. You can't accelerate mass to the speed of light.
I never said that.
Because it takes an infinite amount of mass to accelerate a mass to the speed of light.
Force.
Well, mass, because you have to turn F equals ma, so mass times acceleration. So you get your force from your mass, so you have to burn mass to get to that.
Oh, yeah.
Acceleration.
Okay, I understand what you mean. Yes.
Yeah. So, yeah, Lightspeed is it's so interesting. It truly is, and it's something it's so fundamental, and it's something that we should have this great grasp on, and we just don't. It's such a foreign concept to us. And yeah, I don't know. Do you want me to disprove everything I just said all at once, or do you want to take it slowly?
Oh, we need to ease into it like anal.
Hey, Digger. Hey, I got a freebie. Happy holidays, everyone. Love you, boys. I want to know how we're going to travel without Lightspeed. We're going to get into that as well, because there's all this talk of, damn, Dog Mama, Merry Christmas to you as well with super chat. Thank you, dear. So
Bobby knows
Lightspeed.
what's up.
You don't need to ease in if you prep your hand. Star Trek's transporter was not reality. So we have to think of the actuality of the situation. So our closest star, Alpha Centauri A, is about 4.7 light years away. Do you want to tell them how many miles is in a light year, or you want me to do it?
You do it. I'm just gonna assume I'm wrong again.
You probably are. All right, let me do the math real quick. Shit. Thanks, buddy. I appreciate it.
If you have a specific message you want to put with the $5, let us know.
Yeah, for sure. So let's just use the nice round 300,000.
Million, 300 million.
300,000 kilometers times 0.8 times 4.7.
Oh,
So that is 1,483,207,200,000 miles away to our nearest star. That's not our sun. So that is quite a bit of a distance. So if we take that by the kind of average speed, let's say somewhere in the 35,000 range, is kind of what we've been at max. So, and let's divide that by yeah, we get very small numbers. Oh, nope, because I didn't do it right. So at our current pace, it would take us over 4,800 years to get to there at a max speed of about 35,000 miles per hour, which is more. I mean, we can get there velocity wise, but it's more than we can sustain. And then you're talking about enormous amounts of fuel. You're talking about enormous amounts of energy and wasted. And yeah, like you said, about 70,000 years is the more realistic value. That's if fuel is free, and fuel is something that we can just dig up. Yeah, I'm saying at our max speed that we've ever traveled, for a sustained period of time. So, but yeah, at a realistic speed, it's 70,000 plus years, to get to our nearest star. So when you're talking about distances inside of our own solar system, sun's 93 million miles away. So that's a long way.
The
Right.
universe is not expanding. That was disproven.
Well, it was at one point, and it seems to be contracting now.
Is it back
slightly.
again? What? No. It was consistent. It was found to be consistent.
There's got to be gas stations along the way. We haven't built them yet. So when we take something so, I mean, these are numbers just that we just can't even comprehend. Like, what do you do in 70,000 years? What kind of craft? What kind of, I mean, the people, we don't have, the technologies to be able to even to attempt that. What is that? The average generation is what? Let's say 70. Let's just make it easy. 70 years. Is that fair?
Yes.
If they were stuck on a spacecraft. So we're talking about 1,000 generations. 1,000 generations of humans. And some that would overlap, and I understand I'm just using a relativistic number. We're talking about 1,000 generations. So Mighty signs so much. This topic clearly pisses him off. Thanks, Brian. Sigh so much. No, trust me, Mandy, I am having a blast with this because I really do wish you could have heard the beginning of the show. Brian was so pissed that made me happy right from the get go. I couldn't have been.
Yeah.
I couldn't have been more happy about that. So you take something, and we're talking about 1,000 generations. We're talking about, yeah. I mean, you would have to almost homeostasis or freeze or do something to that effect. So, like, when people talk about going to Mars, so distance from Earth to Mars, right now it's variable because we're both in orbit. And I'm gonna get the actual number. So it says on average about 228 million miles. So even when we're talking about that, we're talking about something that's so far away. It's not going on vacation. It's not going to the next stop. It's not doing anything like this. And then you have to take into account, okay, so even if we could, I have completed the sentence, Mandy. 1,000 generations, that's if nothing goes wrong. Exactly, Jason. So you're taking something and extrapolating it out to where we not only the perfection that we'd have to have with the whole adventure and activity. There's also, what do you do when you get there? Exactly, Bobby. Exactly. So
You couldn't complete that one either.
So at some point you're gonna have to slow down. So all that speed you picked up, you would have to then slow down. So that's gonna take an amount of time. So realistically, we're talking about acceleration, we're talking about slowing, we're talking about all these things. So now we're getting into 100, 150,000 years now, or yeah. And now we're coming up on how far we've been on this planet is to trying to get to another heavenly body. And that's just so, it's just so foreign to us. And we'd never be able to prove something like that. We'd never be able to prove, yeah, we're going to send 10 people on a mission to their death to live out the next 100,000 years and just go hope that they find something. And then you get into the problem, okay, so they found something. They made it 100,000 years. Everything went perfectly. Nothing went wrong.
Are we there yet?
You could, but when we're talking about those kinds of speeds, the gravity is not going to slow it down on its own. So you're gonna need reverse thrust. You're gonna need some kind of retrograde. You're gonna need some kind of you're gonna need something to assist with that. And even if gravitational energy could slow you down, or the gravitational pull of a planet could, then you're still talking about, well, shit, I still have to have the time. I still have to have the time. I still have to have the distance to make that slow.
If you don't have the distance, you become jelly on the inside.
Right.
Have you ever seen the movie Spaceballs?
Yes.
When Darth Helmet goes flying through the freaking console because he was going at plaid.
There we go.
There we go. They've gone plaid, and he flies through the console.
So-
uncontrolled stops, man.
So we're talking about a concept that's so foreign, and then you take in the fact that okay, so we attained 99.85% the speed of light. So what happens to time? This one's for you, Bri.
It dilates and goes backwards.
So you start before you left.
Exactly.
So even if we did get that far, and even if you could approach the speed of light, and even if you could get that close, you would start before you left. Because time dilates and time reverses once we get there. And there's a great study. Exactly. Well, you'd become probably a singularity because of the energy and your mass would, it almost stops and it actually goes in reverse. There's a new study out of I should have grabbed that. I think it's Harvard, where they accelerated light particles to the speed of light, and they were entering the measurement sphere, or they were leaving the measurement sphere before they ever entered the measurement sphere, because time actually reverses once you get to the speed of light. It's a recent study. Let me see if I can find the actual paper. But this is something that I blah blah blah.
I mean, Warsaw and Singapore. That one was back from January this year.
No, this was an American university.
I hate.
Hang on. Yeah, it was Harvard.
It was Harvard? Okay.
Yeah. I was just reading the study real quick. Just give me 1 second. No, that's the one. That's the one where they slowed the speed of light. So they slowed light so that you could actually, converting light. Blah blah blah. So let's take one more step back. Light, particle, or a wave?
Both.
Oh, you did do your research. At least some.
No, it's just a fucking two-slit experiment. We talked about this weeks ago, months ago.
Well, I don't know if you pay attention. So
I don't.
So photons on top of that are interesting because they're massless. That's why they can accelerate at the speed of light. Well,
exactly.
The photon is a massless particle made up of particles of mass.
Yeah, two uppies, one downy. They're called quarks. They're a unit of measurement even smaller than electrons.
Right.
Two up quarks, one down quark.
So we can't even agree and fundamentally decide if light has mass, because it should. It's made of particles of mass, but it doesn't itself have mass, which is interesting, an interesting phenomenon. Like, I don't know. I don't even know what you're better at analogies than me, but
oh God. It think, therefore it am, but it don't think, so it ain't. That's all I got. This one's so hard to analogize.
All right, we're gonna watch a video.
Yeah,
because I need to breathe.
Do it.
All right, so this is supposedly from Yeah.
Many people think that photons, which are essentially light particles, or more precisely, the quanta of electromagnetic fields, do not have mass. But how is this possible? Is there a reason why photons do not have mass? When we look at Einstein's famous mass energy equivalence equation, E equals mc squared, is actually a special case of a slightly longer formula known as the energy momentum relation, which is written out E squared equals p squared multiplied by c squared plus m squared multiplied by c to the fourth power. This equation relates energy,
That makes
E,
sense.
to rest mass, m, the speed of light, c, and momentum, p, which is the key to how photons can carry energy but have no mass. When a particle is at rest, it has no momentum, and the equation simplifies to the more familiar E equals mc squared. But if a particle has no mass, the equation becomes E equals pc. But wait, you might be asking, how can a particle have momentum without mass? That's where light's duality as both a wave and a particle comes into play. Unlike a particle, whose momentum is related to its mass, a wave's momentum comes solely from its motion, meaning that it can carry momentum even without mass. Interestingly, something that has neither mass nor momentum has no energy, which means it is nothing at all. That is, it cannot exist. But
Oh my
photons
god.
do exist, so it follows that they can never be at rest. And the only speed that remains the same in every reference frame is the universal speed limit, c. Light isn't the only massless particle, however.
Please have a man explain
Mass
this.
particles inside atoms also travel at the speed of light. If you want to learn more about space and stay on top of astronomy, news, and updates, subscribe to the channel. Thanks
Shit,
for
no, don't do
watching.
that. Don't subscribe to their channel. Subscribe to my channel.
Yeah, subscribe to Mighty Meat.
Yeah. So,
So,
did that help?
no.
Oh.
So
um,
this is they were literally just explaining the duality of man right here. The it is but it isn't. This is literally going all the way back to the two slit experiment of you have to think of it as both massful and massless.
correct.
And that's not
What's so
helpful.
what's so what's so hard to understand about that, Bri?
It's it, really
So, what if I had an answer for that?
go for it.
Legitimately. We'll 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 get to the answer in just a moment.
Okay.
I think we already kind of touched on space time, correct? Curvature of space time.
Correct.
So when you have something that's hypermassive, like a star or a black hole, it can actually warp space-time. And space-time is theory of relativity. It goes back to Einstein. It goes back to that there's a curvature of space-time. So there's a curvature of space-time.
Yes.
Do you want to explain that?
The best way to explain it is a picture of a massless object. Let me see if I
Yeah,
can find
I was
one.
gonna look for a quick video just because. Why the fuck not? Confuse them a little bit more, right? I mean, help out our chat.
Found it. Found it.
Thanks, babe.
Not a video, but a picture. Whoops. There we go.
Sorry.
Nope, we're good. No, you're good. I was just deleting a whole lot of tabs. So when they say when he says the warping of space-time, imagine this plate on the bottom being time on one axis, space on the other. This being a supermassive object such as a star or a black hole, it will warp it into a dimension that we can't perceive very well.
Correct. Now you want me to tell you that that's wrong?
Yes, I need you to do that for me.
All right. So this is a young lady I know, Sabine, and she explains why general relativity cannot possibly be right. I've never subscribed to this because then you would be on a plane and the planal system doesn't really make a ton of sense to me. But yeah, so this is basically saying that hypermassive objects actually curve the space-time continuum. That's where you get that moniker from. And so in turn, when you're using a heavy object for gravity assist or something like that, then you're actually going a further distance. So, because you're going around that hypermassive object, which is a longer piece. So, time is perpendicular to all three spatial dimensions. Mind bending. Yes. And this whole thing is mostly theoretical at this point because we can't. There's no way to measure this. I mean, could we? Yeah, but we don't. We can't even. I have reached out to Joe about a dozen times. I know, and I would love to have him on, but it's probably not going to happen. So here's Sabine talking about. She's great. Talking about why relativity can't be right.
I want to explain how we know that the way Einstein thought about gravity cannot be correct. Einstein's idea was that gravity is not a force, but it is really an effect caused by the curvature of space and time.
I don't think that gravity is a force either, just for the record. There's a doctor that I know out of University of Colorado that's studying an advanced magnetism as a replacement for gravity, and it shows some promise. Because gravity as a force, 9.8 meters per second on Earth, right?
Yep, 9.8. Yep.
Yeah. It doesn't work out. It doesn't work out when you expand it to either a micro or a macro construct or thought process. It won't go. It doesn't go either way. So
well, the problem is that it assumes that a graviton has mass.
Correct.
Of which we have no proof to show that a graviton has mass to it.
What's up, Josh Chandler? It's that fast, eh?
I was going to say very quick and possibly there.
And very quick and confuses the hell out of everyone.
Matter curves space-time in its vicinity, and this curvature in return affects how matter moves. This means that, according to Einstein, space and time are responsive. They deform in the presence of matter, and not only matter, but all types of energies, including pressure and momentum flux, and so on. Einstein called his theory general relativity because it's a generalization of special relativity. Both are based on observer independence, that is, the idea that the laws of nature should not depend on the motion of an observer. The difference between general relativity and special relativity is that in special relativity, space-time is flat, like a sheet of paper, while in general relativity, it can be curved, like the often-named rubber sheet. General relativity is an extremely well-confirmed theory. It predicts, for example, that light rays bend around massive objects like the sun, which we have observed. The same effect also gives rise to gravitational lensing, which we have also observed. General relativity further predicts that the universe should expand, which it does. It predicts that time runs more slowly in gravitational potentials, which is correct. General relativity predicts black holes, and it predicts just how the black hole shadow looks like, which is what we have observed. It also predicts gravitational waves, which we have observed, and the list goes on. So there is no doubt that general relativity works extremely well. But we already know that it cannot ultimately be the correct theory for space and time. It is an approximation that works in many circumstances but fails in others. We know this because general relativity does not fit together with another extremely well-confirmed theory, that is quantum mechanics. It's one of these problems that's easy to explain but extremely difficult to solve. Here's what goes wrong if you want to combine gravity and quantum mechanics.
Okay, to be fair, nothing really combines gravity and quantum mechanics or quantum theory or quantum field theory or quantum anything. Quantum entanglement. Quantum entanglement's the thought that I can have a particle that accelerates and moves faster than the speed of light, moves information. So if I'm here and Brian's at the edge of the universe and we have quantumly entangled particles, if I flip mine from negative to positive, his will automatically flip from negative to positive. Even if it's a vast amount of distance away, that information between the two moves so incredibly fast that it would flip instantaneously with the flip of my particle back here on Earth. And when you're talking about quantum entangled particles, we have no explanation for it, none whatsoever. But it could be faster than light travel communications if we could exploit them. The problem is there are, God, I can't even think of how many particles. This is your thing. There are ridiculous numbers of particles, and we don't know which ones are quantumly entangled matching pairs.
Buddy, when it comes to anything smaller than a proton, neutron, electron, you're automatically going into theoretical physics.
Well, of course, it's quantum. It's theoretical quantum physics, but yeah.
Quantum
but yeah,
chemistry and all that sticks with the slightly bigger stuff.
So Brian's a one-trick pony. That's what he's saying.
Oh, I'm a pony, all right.
Yeah, ride you, baby.
We know experimentally that particles have some strange quantum properties. They obey the uncertainty principle, and they can do things like being in two places at the same time. Concretely, think about an electron going through a double slit. Quantum mechanics tells us that the particle goes through both slits at the same time. Now, electrons have a mass, and masses generate a gravitational pull by bending space-time. This brings up the question, to which place does the gravitational pull go if the electron travels through both slits at the same time? You would expect the gravitational pull to also go to two places at the same time. But this cannot be the case in general relativity because general relativity is not a quantum theory. To solve this problem, we have to understand the quantum properties of gravity. We need what physicists call a theory of quantum gravity. And since Einstein taught us that gravity is really about the curvature of space and time,
I just like
what
how
we
she
need
says
is a theory
Einstein.
for the quantum
Einstein.
properties of space and time. There are two other reasons how we know that general relativity can't be quite right. Besides the double slit problem, there is the issue with singularities in general relativity. Singularities are places where both the curvature and the energy density of matter become infinitely large. At least that's what general relativity predicts. This
Such as
happens,
a
for
black
example,
hole.
inside black holes and at the beginning of the universe. In any other theory that we have, singularity are a sign that the theory breaks down and has to be replaced by a more fundamental theory. And we think the same has to be the case in general relativity, where the more fundamental theory to replace it is quantum gravity. The third reason we think that gravity must be quantized is the trouble with information lost in black holes. If we combine quantum theory with general relativity, but without quantizing gravity, then we find that black holes slowly shrink by emitting radiation. This was first derived by Stephen Hawking in the 1970s, and so this radiation is also called
Hawking
Hawking
radiation.
radiation. Now it seems that black holes can entirely vanish by emitting this radiation. Problem is, the radiation itself is entirely random and does not carry any information
Jason, we
besides
are.
the temperature. So when the black hole is entirely gone and all you have left is this radiation, you do not know what formed the black hole. Such a process is fundamentally irreversible and therefore incompatible with quantum theory. It just does not fit together. And a lot of physicists think that to solve this problem, we need a theory of quantum gravity. So this is how we know that general relativity has to be replaced by a theory of quantum gravity. This problem has been known since the 1930s. Since then, a lot of attempts have been made to solve it. I will tell you about this some other time.
Thank you, Sabine. So when we take the flip side of that, we know that time dilation occurs. We know that, yes. We know that that's why it just sounds, I really do enjoy it. I do enjoy it. So we know that time dilation occurs because we actually did an experiment. So this is an experiment from, I forget what year, but essentially they put atomic clocks on a plane and the time was different than that of the time that was on the ground. So this is like 2 minutes, but
at $2,300,000.
In 1971, Joe Hafele and Richard Keating put the theory to the test. They flew 4 atomic clocks around the world to compare the passage of time on an airplane with time on the ground.
I don't trust these professors who get up and scribble in front of blackboards claiming they understand it all, because I've made too many measurements where they don't come up with the numbers they say.
Richard had told me that in all the previous work he had done, he had never seen the effect of time dilatation.
I
had never seen it.
I knew what was being predicted and that, but it always seemed to me that the best proof is to measure it.
Hopefully it's going to be available
To see
million
how time
percent getting
slows
struck
down
for
with
this
speed,
music.
They had to travel
100%.
all the way around the world in the original.
Okay, how?
Today's atomic clocks
This was
are
made
more
before Disney.
accurate. The warping of time should be
Yeah.
apparent even on an
It should be
ordinary
public domain.
transatlantic flight.
So they basically,
Yes, one for
Well, I'll
me
tell you
and
about
one for my friend.
About 5 minutes past 4 local time, which is 5 minutes past 9 English time.
Einstein said time is that which is indicated by a clock. I think I know what a clock is, therefore I think I know what time is.
Seem to be following an unbelievably constant.
Before I am.
En route, they collected data from the pilot, then put it into Einstein's equations to predict the time change.
We have accumulated so far a change of 34 nanoseconds. Broadly speaking, it seems to confirm the original prediction. The clock will have gained somewhere between 37 and 40 nanoseconds when we land in about half an hour's time.
So that's impressive. They can measure down
Suppose
to
you
the
would live for
nanosecond.
100 years, and you would spend your entire life on one of these aircraft flying around the world. You could expect to be younger than people who did not do that by about 1/10,000th of a second.
The UTC, USNO Master.
To measure exactly how much time changed relative to time on Earth, the clock on the airplane had been synchronized with the international standard at the start of the trip. Then it was compared to the same standard when it landed in the United States.
If we put other cables in here, that changes by
The clock on the plane disagreed with the ones on the ground by 40 billionths of a second, just as Einstein predicted.
40 billionths of a second. And that's something that they could actually measure. And it's something that they were, like they said, had predicted. So we know that the further you get away from a gravitational body, Earth, time will speed up. And then
Slow down.
excuse me. 40 billionths is, I mean, it's no, but when you're talking about there's excessive time dilation if we get to a black hole. There's time dilation if we get to again this light speed travel. The clocks were not wrong. These are atomic clocks using the cesium, measuring the.
I think they're measuring half-life on the cesium. Yeah,
I think so. So they're measuring something that's incredibly stable to be able to measure down to those very minute details. So have you ever heard of relativity in quantum physics is math? Joe is a lawyer. Lawyers don't do math. Ask him. Yeah. So you've heard of a tachyon, right?
no.
Okay, so a tachyon is the particle that they found that was exiting before it actually entered. It's an intriguing time travel particle. Class of particles, blah, blah, blah. Tachyon particle has almost a mythical air about its scientific community, mostly because we don't know if it actually exists. Like dark matter, which is the biggest cop out. Dark matter does everything and nothing. It's ridiculous. The concept of speed of light, particle travels faster than the speed of light, started gaining pace with Einstein in 1905. Feinberg termed this potential particle a tachyon in 1967. So tachyons. So tachyons travel backwards in time, theoretically. So here's the gist. Right now, we don't know anything that's faster than the speed of light. Light has no mass. So how does it gain size as it speeds up? Meanwhile, an object with mass gains mass as it speeds up, which means it doesn't have enough energy to keep pace with the speed of light. So with everything in our world traveling slower than the speed of light, every cause that occurs within our knowledge in the known universe happens within the speed of light's time parameters. A tachyon, though, is a particle that travels faster than the speed of light in theory. Somehow a tachyon has to achieve constant speed faster than the speed of light, meaning it can never go slower. So tachyons are thought to travel so fast that they actually travel in reverse. So
It's the best way to describe it is if you look at like a what are those the fans, like you're looking at a not a fan but a propeller of like a plane or something. It looks like it's moving backwards because it's moving so fast.
Right.
It's that, but
Yeah.
it's actually moving backwards.
Right. Absolutely.
Yes, I am.
I think Brian is wishing he didn't have to take that shot of Lord. It's not that bad. I took
This
two.
one was not nearly as bad as the first or second time I've taken it because I haven't had it in 6 months.
So
Bobby, it does if you like think about it, if you're looking at the plane rudder instead and then put that to how your life actually works.
Right. He's better at making, what do I call those things?
Analogies.
Analogies. Thank you, dear. So here's the article I was looking for in Science magazine. A quantum time flip. Scientist explains how light can travel back and forth in time. Two teams assist. Let me just share the fucking article. Two teams of physicists recently made a light particle seem to travel back and forth in time simultaneously in their experiments. Stromberg, a lead author of one of those studies, told IE that it's more complicated than light simply traveling into the past. The new findings were from those experiments could help create more powerful quantum computing. What was not a science? What? Scientists made light in the form of a photon particle appear to move simultaneously backward and forward in the time for the first time ever this year. New methods described as quantum time flip was achieved thanks to two principles that form a part of a weird, wonderful, and complex world of quantum mechanics, meaning they describe physical properties of atoms and subatomic particles. Coincidentally, two separate teams of scientists worked simultaneously on a similar problem and released their findings in the same year on October 31st and November 2nd of this year. Unlike photons, they were studying, the two teams were working in the same direction. We reached out to Stromberg, the lead author of the second paper titled Experimental Superposition of Time Directions, to see what it could tell us. For those initiated in the world of quantum mechanics, the idea of particle light simultaneously existing in two different time states likely sounds bizarre, to say the least. It's important to note that we're not talking about a photon literally traveling back in time. So we're talking about superposition, is essentially what they're talking about.
Sounds like they're talking about the two slit, like a new axis on the two slit experiment. It's literally just a wave again.
Quantum superposition. Well, quantum superposition is the thought that it can appear everywhere and nowhere.
Sounds like a wave to me.
Yeah, Schrodinger's cat. Fuck, I can't say his name. Schrodinger's cat. Where the cat's both dead and alive.
Until you observe it.
Right.
So two slit.
So somehow our observation changes things. So how it changes things is still beyond us. So we've kind of been a couple different places today.
True. I don't know.
Can light move faster than light?
Yes.
In what context?
Statistically speaking.
Or in something that we've actually observed. It's called Cherenkov radiation.
Oh, yeah.
So it's the thought of light breaking what we would categorize as the sound barrier. So the blue glow from Cherenkov radiation is similar to sound breaking the sound barrier and creating a sonic boom. So, Schrodinger did not want that to be his legacy at all. At all. It was a joke. It was to basically fuck with people.
But it was so good to describe what he was saying, though.
It was incredibly good and unfortunately, that's what he was known for. But
his dying legacy is a really shitty analogy.
Yeah, I know. He had so many better achievements too.
100%.
And Schrodinger cat was, So I'll read, because I have the book anyways, and might as well get use out of it. But before that, midstream grip, please hit that like button and make sure you're subscribed to the channel. So we'll go through Schrodinger's because it kind of makes sense for those who don't know Schrodinger.
If you want a more in-depth look at it, make sure you go back to one of our previous science. Was that on Tuesday?
Yeah, that was a Tuesday a while ago.
Our old Science Tuesday stream on it.
Yeah, so I'll read the book real quick. The book's theory on it. In the mid-1930s, the Austrian physicist Erwin Schrödinger proposed a thought experiment to highlight how crazy quantum mechanics was. He suggested taking a box in which we place a cat, some lethal poison, and a radioactive source. According to quantum mechanics, we cannot say unless we're checking whether a radioactive atom has broken apart or decayed within a given time. So we must describe it as have both decayed and not decayed at the same time. Only when we check do we force it to be one or the other. Inside Schrodinger's box, the experiment is designed so that any decayed atom will have spat out a particle that triggers the release of poison, killing the cat. Since the cat, said Schrodinger, is made up of atoms, albeit trillions, then it too is presumably subject to the laws of quantum mechanics. So until we open the box to look, we must describe the cat as being both dead and alive at the same time. Only when we open the box do we force everything inside into one or the other state. So that's Schrodinger's cat. I hope no real cats were harmed in the making of this theory. I don't know that he ever did it, did he?
No, he couldn't. Specifically because he was also describing the cat's own atoms being the thing that killed it.
Right.
So obviously, no. He put a cat in a box and said, "See."
Well,
See?
I mean,
He could have stabbed the box, sure.
yeah. Schrodinger believed there was a flaw in quantum mechanics since we never see cats simultaneously dead or alive. One argument states that quantum mechanics says nothing about what the cat feels like before we check. It only allows us to calculate the possibility or probability that we find the poor pussy dead. It says that in the book. Pussy dead or alive when we take a look, or maybe the whole universe splits into two when we open the box. In one, the cat is alive, and the other, it is dead. Oh, fuck. So we're going to go there next? We're going to go to multiverse theory?
See, I prefer the Spider-Verse.
Well, I know, but that's because you're a weeb.
Well, yeah.
That is, well, yeah, because eventually we know that there's a time in which that element decays. Also, unfortunately, cats need food. It was legitimately in the book. Yes. So.
What's the half-life on a cat?
I don't think there's a half-life on a cat. I mean, what's the half-life of carbon?
Is it still a cat, though, or is it just a corpse?
Yes.
Okay.
Isn't that superposition? Yes.
Yes. God, I
Um,
hate this. True. It is tasty. I wouldn't know. I've had Kung Pao chicken.
Chose to use that book because of the wording. No, it's a legitimate, like, scientific book that I read out of. I was just kind of shocked and taken aback by that word.
Back from,
And-
2007?
No, it's a book of theories, and it is from, it's not that old. Shit, now you have me looking at the... Yeah, fuck, you're right. 2009. It's a reprint. It's 2022, but it's from 2009.
God, I'm so good at this.
So, all right, you got me on books. I got you on everything else so far.
Joke's on you, I can't read.
So we'll go back to Cherenkov radiation, because this takes everything that we just talked about and just pisses it all out the window. Because Cherenkov radiation goes faster than the speed of light in the medium of water. So this is a nuclear reactor. And that is Cherenkov radiation, or the equivalent to breaking the sound barrier with sound, as light breaking the speed of light barrier. And it has that blue glow because of the place on the spectrum of the reaction. So I thought that was the other video, but I guess I did the wrong one. So this one's from the International Atomic Energy Agency, and this has an explanation too. Mysterious blue glow is caused by the particles moving faster than light, which is possible in the medium of water or air. The phenomenon is called Cherenkov radiation. And that helps us verify that nuclear material is used peacefully and better understand the universe. Nuclear material is often kept underwater. I guess we don't need this music. The material emits particles which stimulate the surrounding water molecules to give off the unique blue light. Nuclear safeguard inspectors analyze the Cherenkov to confirm the location of radioactive materials. And they work to verify the peaceful use of nuclear material. Astrophysicists can also use the effect to detect particles, blah, 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 which come from distant objects like galaxies, pulsars, and supernova explosions. It still isn't faster than light in a vacuum. Cherenkov radiation is a form of energy that perceived as a blue glow, blah, blah, blah. Moving at speeds faster than the light in our specific medium. Cherenkov radiation is named after 1958 Physics Nobel Prize laureate Pavel Cherenkov, who shared with Ilya Frank and Igor Tam for being the first to experimentally demonstrate and explain this glow. For instance, while in water, light would instantly slow down to 75% of its normal speed, but there's other particles that don't slow down or end up moving much faster than light. When this happens, a blue or violet glow occurs. So,
And that has to do to the wavelength that it uses, right?
Correct. Yeah. So it's kind of like a shock wave, and it gets down into our spectrum here. And obviously we have visible light and spectrum and all that good shit. Oops.
What is the calculation? Lambda C or something like that? C is equal to lambda V. So C is the speed of light, lambda is wavelength, V is velocity, I think, right? Or is that a constant? I can never remember.
I think V is a constant in that, right?
I hate that equation.
Yeah.
V is a constant.
Yeah.
Thus, because lambda is because the water slows down the wavelength of light to being lower than the lambda of this blue color, essentially.
Correct.
Thus, it moves faster. Okay, I understand. So it just doesn't get counteracted by the water. It's a special wavelength.
Right.
Very special, because water's blue. Things that are blue generally don't block blue things.
Mm-hmm. Like lasers in Hawaii.
Like lasers in Hawaii.
There's some conspiracy for you.
Well, no, that's the exact opposite. A red laser won't affect a blue thing.
Oh, is that what that was? I don't know. I just read it at one point, so
yeah,
I didn't know what the hell it meant.
It just gets stopped by it, thus not heating it up. Where interesting. Because wasn't it infrared lights that they were supposedly using from space?
Yeah.
Yeah. IR doesn't affect UV.
Correct.
Thus, blue is UV, pretty much. Well, it's still visible, but it does have some elements that are in UV.
Shit. I was just going somewhere and then I lost my train of thought.
Sorry, I came up with why the color blue.
Where was I going? Where were we before that?
Oh shoot, sorry, I tried to mute myself.
No, you're good.
I apologize, everyone. You were looking at this wavelength.
Oh, I know what it is. All right, talk for like 3 seconds.
Are vampires allergic to UVB? I guess maybe. So if you have lizards in your apartment, then you're safe from vampires because you have UVB bulbs. Thank you, Linda. I appreciate you. But yeah, no. So the reason why the color is blue is, as you know, no matter like whatever color you're looking at, the wavelength of that color, or the wavelength determines what the color is. So it reaches your eyes. If it's more of a wider wavelength, such as it waves slower, then the color becomes more red. And then the faster the waves oscillate, I guess I could say it as, the more purpley it gets. So because it is on the other end of the spectra from what light normally really is. I mean, it's everything, sure, but the one that that a photon would oscillate at is actually going to be more towards the red than these specific these specific particles that we're looking at. Purpley, yes. That is a scientific term, purpley.
Yeah, it's kind of like puffy stuff.
Puffy stuff is definitely a scientific term.
Yeah.
Correct. The blue will well, actually, yeah, because blue's all you're going to be getting through it. So you're going to be blinding everyone.
Correct. See, there's not a good value on this. Maybe
Good
you
value
know.
on
Photon escaping the sun.
like speed?
Like how long it actually takes, because sun's, so we'll just go into it. So some people say, oh, it only takes 7 minutes or whatever it is for light to get from nuclear fusion in the sun to you, and that's not exactly true. Because there's this beautiful thing called solar convection, and I don't know the actual time frame because there's not a good number on it anywhere. But the sun convects and it continues to cycle back through itself. I'm trying to see if there's one. So it continues to go back into the sun and it gets reconvected and goes back through a heating and cooling cycle until it is until it bounces out. So I'm trying to look. Blah blah blah.
But Michael, they wouldn't bounce around if they didn't have mass.
Well, that's why I bring it up. Because you're talking about yeah, I see anywhere from 30,000 to 7 million, and I know that's a wide range, but
In the grand
I'm not
scheme of
seeing a
things,
good
it's not.
yeah. I'm not seeing a good solid number.
It's a factor of 100.
Yeah, I guess. So we're talking about convection and we're talking about radiative and gradients and things like that, which show again that photons should have a mass. They should have some kind of, to have a convective force, they would have to have, like, I understand that they're getting rid of energy, but how are they getting rid of energy into heat if they're not? How are they radiative if there's no mass to radiate?
Because they both have mass and don't have mass. So I'm okay. I'm of the opinion that photons have mass, specifically, like, no matter what.
Yeah.
Specifically because momentum, it does have mass. Anywho, the photon propulsion system that they were wanting to put on satellites would require photons to have mass, and it would have worked.
Correct.
Thus, photons have mass.
Correct. But they also don't have mass. So all
Sure,
that to
if you don't
say,
observe it.
yeah, if you don't observe it, it's fine. Just don't look. Turn around.
Exactly. Close your eyes.
Yeah. So irradiance is now I'm even starting to confuse myself.
Where were we at again?
1 AU spectrum is similar, not equal to Planck function. Radiation comes off layers at different temperatures. Right, but it has to fucking mass. And so when they're saying the solar irradiance spectrum, and when we're talking about the solar flux or the energy that's leaving a particle, part of your equation is mass squared. So how the fuck do you have a square mass if there's no mass to the particle, but there is for solar irradiance? So the energy that is losing during convection has a calculated mass.
Correct. But what's the equation or the units at the end again? It's mass squared over
Looks like nautical miles, or not excuse me. Why can't NM on the spectrum? What? I'm on the spectrum.
wavelength.
There you go. Fuck, I couldn't think of it, and I'm like,
So mass
nautical
squared
miles.
over wavelength.
Right. Yes.
So what that means is that as we approach
Right.
as we approach infinite mass, our wavelength starts getting infinitely small proportionately to give us the perfect speed of light.
But that also, okay.
Of which we say that the mass of a photon is going to be consistent, so we can find that we can find a wavelength if we assume that it's nearly infinity. That's why white light is a thing.
Don't cry.
Fuck. I confused myself.
It's a very confusing topic. But all that to say that it takes a really long time, and we calculate that there is a mass in a particle that's leaving the sun because for our understanding of it, there has to be a mass, or there has to be a value that we can add to a mass. So even if there is no mass, we still have to have a value for the mass to make our equation work out for it to make sense. Is that a good way of?
Sure. Hand puppets, please.
I can't. I don't even know where you would start with the hand puppet.
Well, first we would shove the hand puppet in a box.
So if you're going up in energy levels, you're absorbing electrons.
No, what? Hold on. Hold on. You're talking about electron energy levels.
Correct. Well, I'm talking about photon energy levels, raising your energy level of photon.
So let's macro this a little bit and just go to just an atom, like a water molecule.
I'm trying to not get too deep. I'm trying to have you help me bail it out and make it so it makes fucking sense.
I understand.
People who aren't physicists.
That's why I'm going up a little bit, because as you get
Okay.
bigger, it makes more sense.
Okay.
So in a water molecule, when you excite it, the electrons in said water molecule vibrate faster and jump up in energy level. Thus, when it comes back down, the energy lost actually gets radiated out as light. So the energy gained and lost actually will show itself sometimes as fluorescence. depending on the molecule you're looking at. So we're looking at a massless but massful loss of energy. Goku's energy level is way over 9,000. I think it's like 72 trillion or something like that.
So when you have a transitional recombination of a continuum emission, you get a higher level photon or a higher energy photon.
Correct. Changing color.
Correct. So here's a... God, I don't know if I want to go this way.
Because not all photons vibrate at the same energy.
Correct.
Well, they're not vibrating. They're just moving. I don't want to even think about what a photon would do if it vibrated.
I'm not even... We're good. I'm not going to go there. Because I was going to make a microwave pew pew next week.
What the fuck is vibrating? It literally...
No. I thought we just weren't going to go there.
Okay, I'm sorry. I won't do it. Bobby, go eat a burger or something. I'm not answering that question.
You're talking about exciting photons to get to a higher state, right?
I'm talking about exciting photons to increase or decrease the wavelength of their moving.
Yeah, we're not going to go there.
Because with electrons, you excite them, they go up in energy level, which has something to do with the ability to form bonds, of which then in a photon exciting would be the next level down, which would just change color.
Okay.
Yeah.
Vibrating photons carry D cell batteries. So now that we're way off topic, we're
so far. Sorry.
Way off topic. No, it's fine because this is part of the information and this is part of the depth of this topic. Like there's so much to this topic that we haven't even got close to. And then you take into account the fact that there's so much that we don't understand. And then there's so much that doesn't make any sense. What we can say unequivocally, we have no idea. Like we have no idea. It doesn't fit. And then we're not even taking in quantum properties or anything like that. So but I don't really want to get into like GRBs or anything like that. That could be a whole show on itself.
In and of itself. Yeah.
Like 6 hours worth of show on itself. So let's answer Jason's question, then we'll go back. So if you detonate a nuclear weapon in space, one, it would over 100 years of research and we still haven't figured it all out. Yeah, exactly. And again, my overarching theory is that we live in a simulation and we're not given all the variables to answer these questions. That's my thought. Because it should make more sense, and the best answer we have is it's dark energy, or it's dark matter, or it's blah blah blah. Hey, we've come to a lot of very obscure topics in this last hour and a half that made zero sense too. So give us credit for that.
And you know what? We deserve a whole lot of credit because we're literally a meat man and a guy with a trap avatar trying to explain goddamn nuclear quantum. Not even nuclear quantum. It's just quantum. Quantum mechanics, that's what it's called.
Yeah.
God.
And we haven't even got to quantum mechanics yet. We're still in Lightspeed, which is a relativity principle.
Correct. You're right. Shit. We've gone nowhere. We're making circles.
We are essentially making circles. But so let's answer Jason's question now. So you get into nuclear weapons, so it wouldn't have the compression source of Earth, so you wouldn't have it. You would have a much bigger explosion. Two, depending on how close that you actually set off this warhead to Earth, you would have significant operational issues with satellites. I know that there's many estimates that you could take down nearly all with the right yield of weapon. On the other side of that, we're getting bombarded with solar radiation from the sun all the time. So I don't know. So do you have anything to add on that?
I feel like okay, so when a warhead would explode, the reason why we get a shockwave like we do is because the force from the blast gets knocked into air molecules and other things to stop it, slow it down, etc. Of which this is why you can actually see when a nuclear detonation happens, it will start slowing down its progression outward.
Right, because on Earth it would be essentially going through a fluid and rippling that fluid. In space it would be in a vacuum and it would just dissipate much quicker. I mean, it would continue on and infinitely in every direction.
Right, but I would feel like it would have less force than it would on Earth, specifically because you're not knocking into other things. The amount of mass stays constant.
Yeah.
So, because force is equal to mass times acceleration, when you detonate an object on Earth, you get other mass-ish objects. Oh my god, I can't speak. That's a hard word. Yeah, that one.
Yep.
You get other objects with mass to collide into, transferring the force. So it's basically like a hammer, where you hit it with you'll increase the amount of matter you're hitting it with. Though it's moving slower, it still maintains some level of force in a more direct area.
Correct.
Unlike in space, where it wouldn't do that, it would fan out everywhere. So it would be significantly less probably deadly from 100 miles away than it would be if it was on Earth. But delicate systems like satellites would feel it 100%.
Yeah, because you had a closer effect of higher energy particles that were in direct relation.
Oh yeah, the particles won't lose energy; there'll just be less of them.
Right.
Because there's nothing to slow them down, nothing to absorb any of that force.
Mm-hmm. Yep. And so I wanted to.
Nope, never mind. I'm lost again. Sorry, Digger. Love ya.
Take two or three more dabs, and then call us in the morning. So I wanted to. The people of the past, scientists of the past, are so unbelievably
stupid.
I was going to say special, and not special in a bad way. They were able to come up with so many concepts that are difficult to even recreate at this point, let alone
figgy pudding.
What about figgy pudding?
Literally, they thought that Adam was a fig pudding model.
Well, they didn't get everything right.
Floating.
They didn't get everything right, obviously. this is how they measured light. The Fizeau speed of light method.
What?
And this was in 1894. So we're the time in which we've supposedly measured light. Blah blah blah. I'm trying to get to the experiment. Hang on. He used stellar aberration to calculate the speed of light in a vacuum. In this case, 301,000 kilometers per second and 1728. So damn close. It'd be another 100 years before French scientist Fizeau figured out how to measure the speed of light by means of a terrestrial experiment.
This is actually really smart.
Yeah.
Because he's forcing it to he's forcing it to observe as a particle instead of a wave using the slit.
So I'll explain it real quick. So Fizeau attempted his own measurement of the speed of light. He built an apparatus in which a cogwheel and a mirror were placed 8 kilometers apart, and had sent pulses of light between them. He would rotate the cogwheel and observe how fast the beam of light traveled between the cogs of the wheel and the distant mirror, observing that if he spun the wheel very fast, the reflection back from the mirror was obscured because the light had struck one of the cogs. Fizeau suggested the amount of time that it took for the wheel to move the width of a single cog was equivalent to how long it took before the light beam to travel to the mirror and back again. Since he knew how fast the cogwheel was rotating and the width of a single cog, as well as the distance to the mirror, Fizeau was able to calculate the speed of light, obtaining a value of 313,000 kilometers per second. So he's about 5% away, but this was in 1845.
And you know what 5% was probably? The literal margin of error of how fast his cogwheel was spinning.
Very well could have been, yeah.
That's literally what I'm looking at here. Is it probably could have been that plus just the noise calculation of his observer.
Mm-hmm.
I would write home about that. I would.
Yeah. Foucault improved on Fizeau's apparatus slightly, replacing the cogwheel with a rotating mirror. Hence, now it's known as the Fizeau-Foucault apparatus. Light was reflected at different angles as the mirror rotated. Since both the speed of the rotation and the distance to the mirror were well established, it was possible to measure the difference between the angle of light as it entered the apparatus and when it exited the setup, and calculate the speed from that. Foucault concluded in 1862 the speed of light was 299,796 kilometers per second. So very, very close. No, it's measuring the light that's coming off the light source. So the electricity would be what's going into the bulb. The light would be producing, I assume it would be a tungsten filament light at that time. So the tungsten heats up, it produces light particles or photons, and the photons are measured. So the electricity or the energy is converted to heat and photons.
But so
and radiative.
Not necessarily wrong though, too, because when it comes to the observer, so they're taking measurements at a fixed interval, of which might be, let's say, 20 measurements per second. So it goes for so long that you eventually are able to statistically analyze the situation, and you can extrapolate. You can say, okay, so this is actually what it looks like on a moment by moment basis, not necessarily because so you look at it, right? Like, so say in 1 second you have the first 10 are active, the 11th is not, then the 12th through 20th are active again. That one active one might shift back and forth, like let's say 2 or 3 units or whatever. But it will then go and make a bell curve and say this is what it should be, which would be at the 11th. So you're basically just saying it's a bell curve again of the most optimal, the most it's at, the most issue is at unit 11 or whatever. And then because you can only have so much electricity going through the thing, you can only measure so quickly. So this measurement probably took probably several hundred hours of just running to extrapolate enough data for to gain enough data to extrapolate the result that he got. So not necessarily incorrect, Digger, but I think you're looking at it as electricity when you should be looking at it as just measurement speed in general.
Right. So,
sorry.
No, you're totally fine. And yeah, but we're not trying to confuse people anymore. Damn it, Michael. Everything's fucking photons. It's all radiation. It's just what type of radiation.
Black body.
So yeah, all that to be said. So again, we have this so when you're talking about nuclear physics and you're talking about nuclear bombs and things of that nature, you're using energy equals mass times speed of light. Yeah, you know what I mean. So you're you're using something that, and relativistically, when we're talking about numbers this large and this dynamic and this massive, for something that is not as 1 to 5% isn't going to make that much of a difference in our calculation if we're calculating the yield of a nuclear weapon. If we got to the fact where we were using space travel and needed to slow so we could get into a planetary orbit, or slow so that we could attain that 1 to 5% could be a significant hurdle. And I think that's one of the other things is to even be able to ever entertain that. First, we got to figure out what the hell the speed is. And I think that's a lofty goal and a good place to start is what is our limitation on the actual medium of measuring speed of light. So
yeah, and like a plus or minus of 5%. If we assume we're going to be decelerating at a specific rate, well, that could mean hundreds of thousands of miles over or undershot.
Yeah. It could be not even in the same galaxy. If you're talking about extrapolating it over a distance of 100 light years or 200 light years or 500 light years, I mean, we're talking about values that become so insurmountable in a planet or something that's relatively small compared to universal structures or galactic structures. You're talking about hitting a very small needle, the point of a very small needle from a million miles away, and all that precision will matter at that point. Oh, really?
Oh, I can show you where it hurt me the most.
Where?
No, it's not gonna. Wait, there we go. Right there.
Showing some?
Right on that. No, it's gonna be in chat.
Yeah.
Pull up my little chat there. That's where on the equation it hurt me. right on the differential.
Is that why we became a chemist, or?
No,
Oh.
I just had to go through calculus. I've known I wanted to be a chemist since I was probably a kid.
The calculus book never shoved up my butt. Oh, what?
That's where his physics major stopped right there. Was when he
Oh,
got his book
gotcha.
shoved
Okay.
up his keister.
Gotcha. So yeah, I think that legitimately, does anybody have any questions that we can try and make it more cloudy or more ridiculous? Not you, Brian.
What?
Here, you're typing.
Sorry, I was answering Digger's question.
Oh, okay. So seriously, I mean, if anybody has any questions, feel free. If not, we'll probably work on wrapping up. Can you use the gravity of a planet to slow it the opposite way or the nearest star? Again, we're talking about speeds and so the impact of your gravity wouldn't ever be enough to slow down a vast speed of that nature. So
Too much mass.
Right. So you would be, especially at that kind of acceleration, your mass would be just that of that planet, and there wouldn't be as much force relativistically to being able to slow it down. So it'd be like it'd be really difficult, and it would be really difficult to it'd be really difficult to calculate, for one. That's why when we do something like go around the moon, we have to basically shoot ourselves out there, and then we have to retro burn, or we have to burn in reverse to circularize that orbit and bring it down. Because not even if we shot at the moon, you can't just go land right on the moon. Like, you have to orbit and then touch down, like we've seen with the Apollo program. So even a very small spacecraft like the Apollo program and the gravity of the moon, those forces, even at, I forget what the exact speed is, but let's say 25,000 miles per hour, even at 25,000 miles per hour, which is 1%, 2%, we can't even, that wouldn't even begin to slow us down. So
yeah, no, you overshoot it. You'll get to the next planet before you actually even start slowing down.
You probably get to the next galaxy before you started slowing down.
Yeah, the only thing that'll slow you down is a supermassive object, i.e., black hole.
And then you're dead.
And then you
spaghettified.
get spaghettified. Okay, yeah, we're on the same.
Yes.
Yeah, 100%.
Yeah, that's cool. That's cool. That's neat. A black hole, then a super black hole. So once you enter that event horizon, you're not getting out of it. So once the effects of gravity of a supermassive black hole or a standard black hole would have an effect on the speed of your vehicle, it would pull you into the supermassive black hole, and you would spaghettify and be dead. We can always talk of the simplicity of string theory. String theory has been disproven.
Yes, it has. Thank God.
Thank God, I hate string theory.
String theory is awful.
God, I hate string theory, and it never made a ton of sense. Loop quantum, I can't even say that one. Loop quantum gravity. We kind of touch there. Brain theory, no thanks.
That's way out of my wheelhouse.
All right, so next week, brain theory.
Shit.
And we'll. No, no, I'm not. Not going there. Game theory? We could do game theory.
I know lots of theories about games.
But if it antimatter engines, well, you still have the slowdown problem because your path of acceleration would be equal to because we're not going from 0 to it's not like the movies where you just we're gonna put it in hyperdrive and they move the button and you automatically jump to the speed of light. Like it you have to accelerate to that time, and acceleration to the speed of light is a slow process for something that's mass that has mass.
And if they could, then everything would be completely just destroyed.
Right.
The force, the acceleration needed to get to the speed of light with that mass is so much force, it destroys everything.
Right. It would rip you apart. So if you didn't get ripped apart by the black hole, you'd get ripped apart by that. Now let's say just completely bullshit numbers, just completely theoretical numbers. If we accelerated to 30% speed of light, and we're still taking that acceleration time, and to accelerate would take 8, 10, 15 years. So, because it's got to be a gradual acceleration. One, because materials can't take that force of gravity or the force of acceleration past a certain point. So it would still have to be a very, very gradual acceleration all the way out. See, string theory understood, but then Mighty said you're disproving it. Now I don't know where to go. String theory has been disproven by a lot of physicists over the last so on and so forth. It was never terribly sound, and they never really had a ton of supporting evidence for it, in my opinion, at least. So it's kind of like dark matter, where it's just there's something there. You what?
It's an answer to a variable that they couldn't figure out the true answer, so they just made one up.
Exactly.
To make it work.
Here's one. If gravity is a particle and c is the max speed, then the event horizon is at the point at which nothing faster than light can exist. How does black hole exert gravity? So we're assuming gravity is a particle, because I don't think gravity is a particle.
Well, we would have to in this case. We would have to consider it the same as a photon, where it can both be observed as a light and a wave, or as a particle and a wave.
Okay.
But, and if assuming that it's a wave, it won't have any problem like leaving a black hole, because it's just a force. It's not
right.
It's not a massive. It's not a massful object. I can't say massless. Oh, hey, I said it.
I'm gonna give you the scientist answer. Dark energy.
Black.
Dark energy, obviously, it obviously speeds past the speed of light. So,
it's African American gravity. It's not dark matter anymore. Gravitons are proven, sorta.
It'd be gravity based on how does it exert gravity? It'd be gravity based on the I'm going to think about it for a second.
So with gravity, they make a couple of assumptions. One, it has less mass than light.
Right.
They have to. It's a fundamental thing, because it has less mass than light. Light is less affected by it than it is affected by light.
So I think you'd have to go back to relativity and say that there's a space-time component to it, where it would slow time, and time would trump the speed of light.
No, less mass, Michael, because we assume that light for gravitons to exist, you have to assume that light has mass. So if you assume that light has no mass, then gravitons don't exist. But gravitons are an assumption based on the fact that gravity has a wave to it. All right,
Negative mass. So if you're talking the matter antimatter paradigm, then of course you would have a negative mass, and maybe it could be annihilating, and that's why we can't see anything. Maybe that's why there's so much radiation coming out. I'm just spitballing, but could it be annihilating? I don't know.
No.
So waves have no mass.
Correct.
A wave shouldn't have a mass. A particle would have mass, but a wave is...
A wave would be none.
Right. Go straight chat GTP. Gravity is not the speed of light, but a fundamental force of attraction between objects with mass. Yeah, well...
That was literally just disproven, though, because it was a wave.
Right.
Outdated GPT.
Very much so.
That's actually what's taught in textbooks. That's ripped straight from a textbook.
Yeah. And so I think that's another interesting thing, and something that I learned in academia, and then in spending time with actual scientists, is that the book teaches just enough for people to grasp and understand the concept. But when you get into the theory of the concept, it goes so much deeper, and it's so much more obscure than is what's taught in your textbook. So your textbook is a basic representation of something that people that are on an entry or even an elevated level are going to be able to grasp as concepts. And then when you get into the theoretical side of it, it becomes much more of a thought game, where much more of the truth, I guess, is revealed. You would agree with that, right?
Yeah.
I don't know if that's how it is in chemistry, but that's how it is in...
You scratch the surface and you just get deeper and deeper and deeper until you eventually will hit a point where you're just, this might exist.
Right. Attraction needs an exchange of either information or a particle or both. So why can't they annihilate and accumulate mass from the radiation? You completely just fucked me on that one, but why not?
God damn it, this is way out of my pay grade.
I mean, I've never seen any literature that suggests that there's an annihilation and an accumulation of the energetic mass that's unleashed because of it. However, no, I'm not going to go there, because then we're going to get into gamma ray bursts and stuff like that, and we can't do that tonight because we only have like 9 minutes left. But do you see where I'm going with this?
Yes.
Yeah,
no, we're not going to touch that with a 50-foot pole right now.
Attraction being the explanation for gravity. Well, so I think this is a hard question, legitimately, Michael, sorry, for me to answer, because I don't believe in the fundamental force of gravity. Like I've seen enough information and like I said, worked with a doctor out of Colorado and looked at a lot of his research, and I don't believe that gravity is a fundamental force, and I don't believe that gravity works in a lot of application. It works in very limited applications, but Newtonian gravity is so far from it's more like that the scientific understanding where you get taught Newtonian gravity, but then when you apply Newtonian gravity to physics, it all falls apart. So we remain on Earth more so, in my opinion, from the 14 pounds per square inch that's pushing down on us from our atmosphere. Right? Yeah, 14.7 pounds per square inch. I mean, there are hundreds of. Well, I don't know what that would. There are significant amount of weight of fluid that is above your head that's holding us in through.
We may have a disagreement about that one, but that would be a very. I would have to formulate an argument for that.
Well, that's why non-spinning core planets don't hold atmospheres. Because there's an electromagnetic component to gravity.
Again, I would have to fucking think about that one, Chief.
I've studied that one extensively, so
that's a Rocket Man kind of thing, not a I'm gonna make meth kind of man.
Yeah, exactly. They don't teach that in the hood. That's not hood science.
They don't. It's not a hood science, 100%.
But yeah, so we do have a typical pressure of 14.7 pounds per square inch. Have you guys ever seen the imploding can, so we can leave with something that's funny or at least cool?
I prefer the imploding fuel tanker.
There's a really good one that somebody did, and I've showed it before.
Oh, are you talking about the bottle?
No.
Oh, the imploding mini sub? Uh-huh.
No. No.
Linda was right on point.
It's a big tank. I'm looking for
Ghostery. I said I was groomed by a professor.
That's kind of what I'm looking for, but I don't want to use TikTok.
TikTok. I'm highly debating on calling in a freaking noise complaint among the fuckers underneath me. Again.
Oh, that sucks. Again? Tonight?
Well, no, not tonight. I haven't done one I haven't done one ever. I complained to my complex, but like these fuckers will play like loud ass bass boosted music until like midnight.
That sucks. Did you tell me you're like 65? You can't deal with that shit?
True. Well, actually, so because I grew up with like negative amounts of sound around me, I can't sleep with a whole lot of extra sound. It's pretty sad.
Huh. So this is a pretty good one. And this is just from atmospheric pressure. So we'll end with this, but
What if we remove the air from something a whole lot bigger than an egg or a marshmallow? like a 150-gallon drum. So what we have here is a gigantic barrel. Right now, it's filled with water that we've been boiling for quite a while. And so as the water is boiling, it's evaporating and it's pushing the air out of the barrel. And so now it's just really filled with mostly steam. So Nick is going to cap the barrel at the end and lock all the steam inside. Then we're going to cool it down and we're going to see what happens to the barrel and the water inside. Anybody?
So they're allowing the fluid inside to condense and take up less volume, so the atmospheric pressure works on the outside of the tank and implodes it, basically.
Have any predictions?
That was for the sake of copyright.
Something's gonna explode.
Something's going
You should
to
get the thing that
explode.
causes it to flip
Okay.
upside down.
That's a fair guess, given what.
What'd you say?
There's an add-on that can flip this upside down, and like the YouTube overlords don't find it as quickly.
Oh, really? Huh.
Yeah, I'll find it for you.
Yeah, it's not worth it. I don't monetize shit anyways. It's just not worth the hassle.
What we usually do. Well, Nick, are we ready to find out?
Ready to go, Kevin?
That was dramatic. All right, let's go.
All right. You're not going to roll it?
All right, we're going to start cooling this down. So now, all that water vapor inside is condensing as it's cooling back into liquid.
And it's still capped, so there's no way for air to get back in there.
And hopefully, the barrel will cooperate. And if it doesn't, Nick, it's your fault.
Yes! So that's from atmospheric pressure. No, I implied that gravity is not traditional Newtonian gravity. I said we're helped by staying on the planet because of atmospheric pressure. Mirrored stuff is an excellent tactic to fight against the MCA. Oh, I didn't know that. Huh.
Submarine implosion demo. True. The only difference is there's no
Some of the
PS2
water that
controller.
was resting on top of the barrel kind of just sat there as the implosion happened and it went back down, while other parts of the barrel shot water back up into the air. So you could see patterns outlining how the barrel imploded by the water and the.
Okay, we don't need to hear his explanation, but great beard. No worries, buddy. Yeah, no, I'm talking about more of the spinning core creating an electromagnetic force that would simulate gravity. But anyways, I thought this was a hell of a topic, Bri. I appreciate it.
This one's rough.
I had fun taking you to Pound Town. So
Yep, I feel pounded.
well, we'll talk about next week's, but maybe I'll give you a leg up. We'll do a chemistry topic if you want.
Oh, no, Albert. Well, maybe I'll have to think of a topic then.
I'll just sit here and look stupid.
True.
I'll be the waifu next week.
You mean the trap?
Yeah. Oh, yeah. Trapu.
The trap.
Snafu? I didn't say it.
You didn't. I heard nothing.
But, ladies and gentlemen, I want to thank you for dealing with our ridiculousness. Hopefully, you actually legitimately learned something today. We tried. It's difficult. It's very difficult to explain. It's even more difficult to nail down because a lot of this is not settled yet, and a lot of it we have a lot of work to do till we can get to some place where it is. So, I want to thank everyone for hanging out. And from Brian and I both, we wish you a very, very Merry Christmas. If we don't see you before then, hopefully everyone's safe and has a very, very good holiday season. So. No.
Merry
Brian just said
Christmas,
fuck off.
everyone.
Brian says fuck off.
I didn't know. I thought.
Let me begin by wishing you all a very Merry Christmas. Remember the word?
Thank you, Mr. President, because Brian's an asshole. But
I thought you were speaking for me as the obvious bottom in this relationship.
but no, for real, yo. Have a very Merry Christmas. I will be doing the launch of the Sarah 2 mission tomorrow morning at 7:55 a.m. Eastern Time.
Ooh.
Yeah. German refractory satellites.
Like
Defense
me with my
contractor satellite,
refractory period.
which is almost negligible. Like
It's true.
It is so impressive. But yeah. I'm trying to stall because I'm trying to send everybody over to Kaiser's, but
all right, check out my channel Nucleated Gaming. I just put out the Alex Jones video like 2 days ago or yesterday or whenever.
And it's funny. It's funny. So
I get to fight gay frogs.
It is. So hope everybody has an awesome night. Merry Christmas, everybody. And I will see you guys all again very, very soon. Take care, y'all.